Tonight, we're going to explore what is actually preventing us from colonizing Mars. For more than a century, Mars has looked like the nearest thing to a second Earth. It is cold, dry, and hostile, yet familiar enough that scientists and engineers now speak seriously about doing more than visiting. They speak about staying, but reaching Mars is not the true barrier. Neither is planting a flag or keeping a small crew alive for a few months. A colony must continue functioning when equipment breaks, supplies run low, and Earth cannot intervene. It must produce air, recover water, generate power, grow food, protect its residents, and replace the parts that keep every system alive. A settlement that depends on Earth for every emergency is not a second home. It is an outpost. That distinction matters because Mars is often described as an insurance policy for humanity. One planet leaves every human life and achievement exposed to the same catastrophe. But an insurance policy only works if the second world can survive when the first can no longer help it. Before the first settlers arrive, machines may need to build shelters, establish power, extract water, and prepare the systems that will keep them alive. Afterward, those systems must endure radiation, isolation, toxic dust, and storms capable of covering the planet. By the end of tonight, you're going to understand why getting to Mars is only the beginning, what must be built before a permanent settlement becomes possible, and why true colonization begins only when human life there no longer depends on constant rescue from Earth. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Mars earned its place in this dream because several of its basic rhythms feel strangely recognizable. It turns once every 24 hours and 37 minutes, close enough to an Earth day that the human body could probably adjust. Its axis is tilted in a similar way to Earth's, giving the planet spring, summer, autumn, and winter, although each season lasts far longer, because a Martian year is nearly twice as long as ours. Underfoot is solid rock and dust rather than a bottomless atmosphere. Above is a sky with clouds, winds, frost, and changing light. Ancient channels cut through the landscape, marking places where liquid water once moved across the surface. None of that makes Mars comfortable, but it makes the planet recognizable enough for one dangerous thought to take hold. Perhaps this is a place where human life could be reconstructed. That idea is older than spaceflight itself. In the 19th century, astronomers studying faint markings across the Martian surface concluded they were seeing canals. Some believe these were engineered waterways built by an advanced civilization carrying water from the polar regions across a drying planet. Given the telescopes available at the time, the idea was not as absurd as it sounds today. Astronomers could not reliably distinguish a narrow surface feature from a shadow or an optical illusion. Where instruments failed, imagination filled the gap. Maps were drawn. Papers were published. In 1911, the New York Times treated the possibility of a Martian civilization seriously enough to discuss it in print, as though confirmation might arrive with the next generation of telescopes. No canals were ever found, but the question behind them survived. It simply changed from whether someone already lived on Mars to whether life had ever existed there at all. NASA's Viking landers arrived in the 1970s, carrying experiments designed to test Martian soil for signs of living organisms. The results were ambiguous, and the missions that followed adopted a more cautious strategy. Instead of searching directly for life, they searched for the conditions that could once have supported it. Rovers studied ancient lake beds, sediment layers, channels and minerals formed in the presence of water. The question became geological. Was Mars once warm enough, wet enough, and stable enough for biology to begin? Perseverance pushed that search further by exploring an ancient crater lake and collecting samples from rocks that may preserve evidence of past microbial life. Those samples are not proof that Mars was alive, but they come from places where the ingredients and conditions for life may once have existed together. That possibility helped transform Mars from an object of scientific curiosity into a proposed destination. Organizations such as the Mars Society and Mars One formed around the belief that settlement was not merely a distant thought experiment, but an engineering project that could be started. Governments and private companies followed the same pull, drawn toward the only nearby planet with a solid surface, a familiar day, accessible ice, and at least some of the raw materials a settlement might use. The argument gradually shifted. Mars was no longer valuable only because it might answer whether life began twice in one solar system. It became valuable because it might offer humanity somewhere else to exist. But here is where the motivation stops being about curiosity at all. Roughly 6 billion years from now, our sun runs out of the hydrogen it burns for fuel, swells into what astronomers call a red giant, and expands far enough outward to swallow Mercury, Venus, and very likely Earth along with them. Every ocean boils away first. Every trace of everything we ever built goes with it, unless something of us already exists somewhere else by then. That is not a threat anyone alive today needs to plan around personally, but it is not a hypothetical either. It is closer to a certainty on a very long clock. Long before that clock runs out, on a timescale of tens of thousands of years rather than billions, a second threat is waiting, one with no fixed date at all. A large asteroid, the kind capable of ending a dominant species the way one ended the dinosaurs, is statistically overdue. It could arrive in 1,000 years. It could arrive tomorrow. No one watching the sky can rule either out. Colonizing Mars, seen this way, is not a hobby, not a curiosity project, not an adventure for people who already have everything else solved. It is insurance. Spread life across 2 worlds instead of one, and a single asteroid, a single catastrophe, can no longer end the whole story in a single afternoon. It is the same logic that keeps a person from putting every dollar they own into one basket, except the basket here holds every human being who has ever lived, and everything any of them ever made, every language, every discovery, every memory of every person who came before, not putting all our eggs in one basket. That is the whole argument, reduced to its simplest form, and it is why the question of a second home outlasts every other reason anyone has offered for going. That reframes everything that follows in this piece. The question is no longer whether Mars would be worth visiting on a good telescope night. It is whether we could actually build somewhere to live there, permanently, using technology that, in many cases, does not fully exist yet. Autonomous machines capable of raising a habitat without human hands anywhere nearby. Shielding that can hold back radiation for years at a time without weighing more than a rocket can lift off the ground. A steady supply of breathable air, drinkable water, and edible food manufactured from a planet that offers none of those things for free. Answers for the isolation, the low gravity, and the storms large enough to blot out the sun for weeks. None of that is settled yet. Most of it is still being built, tested, or argued over in laboratories on Earth right now, long before anyone boards a ship bound for the red desert overhead. Whether humanity is actually ready for any of it is the open question this whole piece sets out to test, one unsolved problem at a time. And reaching Mars in the first place, before any of that technology even gets a chance to matter, turns out to be its own kind of problem. That problem starts with 3 months, more or less, which is how long the trip to Mars takes under the best possible alignment of the 2 orbits. 3 months does not sound like an especially difficult number. It sounds like a long cruise, the kind that used to carry passengers across an ocean before airplanes made the crossing pointless. Weeks of open water with nothing but routine and patience standing between departure and arrival. Framed that way, the crossing sounds almost gentle, a stretch of boredom to be managed rather than a hazard to be solved. But there is a difference between a cruise ship and a spacecraft that most people never think about until someone points it out. A ship on Earth's oceans stays inside Earth's magnetic field for the entire voyage, wrapped in the same invisible shell that protects everyone standing on dry land. A spacecraft bound for Mars leaves that shell behind within days of launch and does not get it back until the crew either steps onto solid ground on the other end or turns around. For at least 3 months, every person on board sits directly exposed to the solar wind. The steady stream of charged particles the sun throws off constantly, along with the wider radiation drifting through open space with nothing between it and the human body but a thin hole. That exposure is not a minor discomfort. Sustained enough, radiation of this kind has been linked to cancer developing years down the line, long after the mission itself is finished. It has also been linked More surprisingly, to symptoms resembling Alzheimer's, a disease usually associated with old age and with nothing at all to do with a spacecraft cabin. The link is still being studied, and the exact scale of the risk is one more thing this whole undertaking cannot fully answer yet. But the direction of the evidence is not in question. 3 months exposed to it, and the crew has not even reached Mars yet. So the ship needs shielding, and the options split in two directions. The first is straightforward if unglamorous. Build the walls out of something rich in hydrogen. Since hydrogen atoms happen to be unusually good at absorbing the kind of particles this radiation is made of, breaking their path before they ever reach a person inside. Water works for this better than almost anything else available. Line the crew cabin with a water tank, and the water does double duty. Drinking supply on one side of the equation, shield on the other. No extra mass wasted on a job that could be done by something the crew was carrying anyway. The second option is more elegant on paper and much harder in practice. Generate a magnetic field around the entire spacecraft. The same trick Earth performs for free on a planetary scale, shrunk down to the size of a ship. It would work, in principle, the same way it works for the whole planet, deflecting charged particles around the hole instead of letting them pass straight through. But here is the problem. A field like that needs a genuinely large amount of power. Far more than solar panels or batteries could realistically supply for months at a stretch. And the reactor compact enough to produce that power while still fitting inside a spacecraft does not exist yet. Not as a blueprint on a drawing board. Not as a working prototype sitting in a lab somewhere, waiting for funding. Not yet, in any form anyone has actually built. It is the same gap this whole survey keeps circling back to. A solution that sounds reasonable on a whiteboard and simply is not available in hardware yet. So for now, the water tank remains the more realistic answer of the two. Radiation is only half of what the crossing costs. The other half is silence or something close to it. On Earth, distance barely touches a conversation. Call someone on the far side of the planet and the delay is a fraction of a second, short enough that nobody notices it happening. Light moves that fast. Fast enough to make the whole planet feel like one room. Close enough that a conversation feels instant no matter how many time zones separate the two people talking. Stretch the same signal across the distance to Mars though, and light stops feeling fast at all. Depending on where the two planets sit in their orbits at the time, a radio signal takes anywhere from about 3 minutes to 22 minutes to cross the gap, one way. Send a message and wait for the reply, and the shortest possible round trip still runs to roughly 6 minutes. About as long as it takes to hard boil an egg from a cold pan of water. Not a phone call. Nothing resembling one. A question and its answer. Minutes apart at best, and often much longer than that. Text, audio, and recorded video can still cross that gap without much trouble. But a real conversation, the kind where one person answers while the other is still listening, cannot. And the delay does not shrink for emergencies, no matter how urgent the moment on board happens to be. If something breaks, if a system fails at 2 a.m. ship time, there is no engineer on Earth who can talk a crew member through it as it happens. The fastest anyone on Earth could possibly respond is 6 minutes away, and by the time a reply even arrives, the situation on board has already moved on without it, resolved one way or another before the advice shows up. Mission control becomes an audience to what already happened, not a rescue service standing by. So the crew has to be two things at once before they have even landed. Hardened against radiation they cannot see or feel arriving, absorbing a risk that only shows itself years later, and entirely on their own for anything that goes wrong in the moment, with no expert voice reaching them in time to matter. Both conditions start the moment the ship clears Earth's magnetic field, and neither one lets up until the crossing ends. No amount of training back on Earth changes either fact, only how well the crew is prepared to live with them for 3 months at a time. That was only the first problem, and it started before anyone had even chosen a place to land. Choosing that place turns out to be its own tangle. No single site has won out yet over all the others, and there is a reason for that. Every candidate wins on one count and loses on 2 more. Start with water, since nothing else in this whole undertaking works without it. Mars keeps almost none of it in a form anyone would call familiar. The atmosphere is too thin for liquid water to sit on open ground for more than a moment before it boils away or freezes solid, so whatever water exists has to hide from that thin air. It hides as ice. The North Pole holds one obvious answer. Its polar cap carries water ice, layered and frozen, sitting out in the open the way a glacier sits on a mountain range back on Earth. A colony built near it would have water close at hand. Nothing to drill for, nothing to dig out from underneath anything. So, why not just settle at the pole and be done with it? Because the same high latitude that keeps that water frozen and within reach also weakens the sunlight falling on anything nearby. A colony out there would have water on tap, and barely enough sunlight to run the equipment keeping everyone alive on it. The Korolev crater offers a second answer, farther from the pole but just as cold. It stretches 81 kilometers across, roughly the distance you would cover driving for an hour and a half on an open highway, and the whole floor of it holds water ice packed down at the bottom, where the temperature never climbs high enough to let it go. The atmosphere above the crater is still far too thin for that ice to ever pool into a lake on the surface. It survives only because the crater floor stays permanently cold enough to keep the water locked solid, hidden from a sky that would otherwise take it. But here's where it gets strange. Surface ice is not the only water on the planet, and it may not even be the best of it. Underground, beneath the crust, permafrost holds water too, spread across the planet in patterns scientists have only recently begun to map, piecing together readings gathered by multiple orbiters circling overhead, none of which can see straight through rock on their own, but which together, layered against each other, sketch out where the frozen water sits. This buried water sits closer to the equator, in warmer latitudes where sunlight lands more directly, and solar panels would actually produce something close to their rated output. But it is also buried. Reaching it takes drilling and machinery that surface ice never requires. Equipment that has to be hauled across the same distance as everything else the colony will need. So, the two best water sources point in two different directions. One sits at the cold pole, right out on the surface, easy to reach and nearly useless for solar power. The other sits underground, near the equator, harder to reach but paired with far better sunlight for running a colony's systems. Wait, there's a third pole still to come, and it has nothing to do with water at all. Landing a spacecraft safely adds that pull, and it points somewhere else again. A spacecraft slows itself by pushing against air on the way down, not unlike a parachute settling a jump on Earth. More air pushing back means a gentler landing. Less air means a harder one, because there is less there to fight against. And the amount of air stacked above any point on Mars depends on how low that point sits. The same way water gets deeper the closer you sink toward the bottom of a lake. Low ground carries a taller column of atmosphere above it, thin as that atmosphere already is everywhere on the planet. High ground carries less air still, barely enough to slow anything at all. That thicker air sits over Mars's northern hemisphere, where the elevation runs lower than almost anywhere else on the planet. The map does not line up. Not the same latitude as the best water, not even close. The safest place to land a spacecraft, and the easiest place to reach water on Mars, are not, on any current map, the same place. You would think a colony simply lands where the water is. It does not work that way. Mission planners have mostly settled on a compromise instead of chasing one perfect answer. Pair a low elevation, northern landing zone, chosen for the thicker air cushioning the descent, with reasonable proximity to an equatorial water source that has to be drilled for rather than found sitting in the open as ice. Neither the ideal water site nor the ideal landing site wins outright. Both get partly sacrificed so the mission can survive its own arrival before anything else about the colony even begins. It is not the answer anyone would draw up on a blank map with no constraints attached. It is the answer that survives contact with all of them at once. One more factor still shapes the choice, and it has nothing to do with water or air at all. It is what waits underneath the ground. A lava tube is a long cave, formed when a river of molten rock drained out from beneath its own hardened crust, and left the empty tunnel standing behind it, the rock above cooling into a roof, while the rock beneath simply flowed away. Earth has them, cooled and hollow in old volcanic country, some large enough to walk through standing upright for miles. Mars has them too, and orbital imaging has already turned up candidates scattered across the planet. Some of the Martian tunnels wide enough to fit entire buildings inside, roofed over by solid rock nobody had to pour or print. A tunnel like that offers something no printed habitat can match on its own. A roof that has been standing since long before anyone thought to go looking for it. Whether any given lava tube sits close enough to the chosen water and the chosen landing zone is a separate question, asked all over again for every site under consideration. These same tunnels will turn out to matter for more than shelter alone, but that thread waits for later. For now, no single site has won. The best water is not where the best air is. The best air is not where the best shelter is. Whoever draws the final map still has all three of those pulling in different directions at once. And wherever that map finally settles, someone still has to build there, years before a single colonist ever sets foot on the ground. With a spot chosen, the next problem begins, and it begins years before anyone lands. A single spaceship cannot carry everything a colony needs to survive its first year, let alone the years after that. Habitats, power systems, life support, none of it fits on one trip, and none of it can wait for human hands to assemble it on arrival. Forerunner missions have to lay the groundwork alone, on a world where no one is there yet to help them if something goes wrong. Architects and engineers have spent years competing to design what that groundwork should even look like. Entire competitions have run on exactly this question, teams submitting habitat concepts to be judged against each other. There is still no single winning design. Some proposals build with ice, packed and shaped into walls thick enough to hold. Others borrow the structural logic of fungi, branching, self-supporting, grown more than built. But most proposals converge on one material because it is the one material Mars actually hands you for free. Regolith, the loose, broken rock and dust that covers the entire surface, the same fine grey material every rover has driven across since the first one landed. No competition has produced a single agreed answer. The field is still wide open. The plan is to excavate it, process it, and mix it with water ice until it behaves like something similar to concrete. Then print it, layer by layer, the way a 3D printer on Earth builds up an object one thin pass at a time. Except the object here is an entire habitat, and the machine doing the printing has to work alone, outdoors, on ground no one has ever built on before. But here's where it gets strange. Those robots do not exist yet. Not as a rough prototype sitting in a lab, not as a scaled down test model running trial prints on a warehouse floor. The autonomous construction robots this entire plan depends on have to be invented before the plan can even begin. Everything downstream of them, the habitat, the burial, the pressurizing, waits on a machine nobody has finished designing. That gap matters more than it sounds like it should. Once astronauts do arrive, they cannot simply pick up the work by hand where the robots left off. They live inside pressurized suits for every minute they spend outside a sealed structure. Hard, prolonged physical labor, hauling material, lifting, shaping, digging, in a suit like that, on ground like that, is not just difficult. It is close to impossible for a human body to sustain for long, which means the heavy construction has to be finished, or nearly finished, before the first human foot ever touches Martian soil. Robots build the house, people move in after. Ask why not simply send people first, and let them direct the work in person. The suits answer that question on their own. A body sealed inside one for hours at a stretch, moving against its own resistance with every step, cannot excavate, mix, and print a habitat the way an unencumbered machine can. The order is not a preference, it is close to the only order that works. Say the robots exist. Say the printing works exactly as planned. The building still is not done once it is standing. It still needs a roof over its roof. Regolith gets piled on top of the finished structure, shoveled on in thick layers, and not for insulation, and not for looks. For radiation. Mars carries no magnetic field of its own. Nothing wrapping the planet the way Earth's field wraps ours. So radiation that would never reach someone standing in an open field back home reaches the surface here freely, day and night, with nothing overhead to turn it aside. The only real defense against that is mass. Simply putting enough material between the sky and the people underneath it. More regolith piled on top means less radiation getting through to anyone sleeping beneath it. It is not an elegant solution. It is an effective one. And on Mars, effective is what actually gets built. So the sequence runs print, then bury in that order every time. A building shaped by machines, then buried by the same machines, standing finished and hidden under its own planet before a single colonist has arrived to see it. When colonists finally do reach the surface, the habitat waiting for them is not finished in the way a finished home is finished back on Earth. Power still has to be connected. Equipment still has to be unpacked, set up, and tested. The whole site still has to be brought fully online, piece by piece, by the same people who just spent months crossing tens of millions of miles to reach it. In the meantime, they live somewhere smaller. Their arrival craft, still sitting where it landed, or an inflatable shelter pressurized just enough to keep them alive. Not spacious, not comfortable. Built for survival, not for staying. A placeholder home while the real one comes fully online around them. Only once the permanent habitat is sealed and tested does it get pressurized into something closer to a livable home. Breathable air does not arrive shipped in tanks from Earth, not in any quantity that could last. It gets made on site out of what the ground and the ice already provide. One method for producing it uses electrolysis, running electricity through water to split it into its two component parts. The same basic reaction you could demonstrate in a classroom with a battery and two electrodes dipped in a glass. Oxygen collects on one side, hydrogen collects on the other. The oxygen gets mixed with nitrogen to make air a human body can actually breathe, at a pressure the lungs recognize. The hydrogen does not go to waste either. Refined further, it becomes hydrazine, usable as fuel for later missions. And once that sealed air fills the habitat, it does not just sit there and slowly go stale. It gets cycled and scrubbed continuously by recycling systems already proven on the International Space Station. Systems that have kept astronauts breathing the same air, cleaned and reused, for years at a stretch in orbit without failing. Every piece of that sequence, print the structure, bury it, wait for the crew, pressurize it, depends on hardware that either does not exist yet or has never been tested at this scale. This far from anyone who could step in and fix it if it failed. The habitat is not the hard part because building is inherently hard. It is the hard part because almost none of the tools needed to build it have been invented yet. No definitive design has even been chosen. The robots that would carry one out are still, right now, only sketches and lab prototypes. Those construction robots do not exist yet, but the machines that would make them possible are already learning to walk. Walking is not new. Wheels solved that problem for Mars rovers decades ago, or seemed to. Spirit, Opportunity, Curiosity, Perseverance, and China's Zhurong all share the same basic shape. 6 wheels. A boxy body, some standing over 2 meters tall, about the height of a tall doorway, packed with cameras and instruments. The design makes sense. Wheels roll easily across flat ground, and a bigger frame carries more equipment. Form follows function, but wheels have a weakness. They get stuck. In 2009, Spirit rolled into a patch of soft, sun-cracked sand and could not get free. It spun its wheels trying, burning through its batteries in the effort, and the mission that had already outlasted its planned lifetime by years ended there, half buried in Martian dust. There was no tow truck to send, no cable to winch it out. A machine built to survive cosmic radiation, punishing temperature swings and years of dust storms, was stopped cold by something as ordinary as loose sand. Opportunity hit the same kind of trap in 2005, but pulled loose again within about a month. Earlier in that same mission, Opportunity had driven down into Endurance Crater, where exposed rock along the crater walls held some of the clearest evidence anywhere of Mars's watery past. The rover's driving limit was a slope of about 30 degrees, roughly as steep as a black diamond ski run, and engineers were not certain it could climb back out. They sent it down anyway. It climbed out. It kept working. 15 more years of driving followed. 15 years of science the crater almost took first. Spirit did not break down. It got boxed in. Not a mechanical failure. A geography problem. And geography does not care how well built the rover is. A different design was already being tested on Earth, one that did not need a flat road at all. Boston Dynamics built Big Dog first, a four-legged machine that could cross powder snow and climb slopes no wheel could manage. The same company later built Atlas, a humanoid robot that runs, jumps, and climbs almost like a person. But the machine that caught NASA's attention was a smaller cousin of both, Spot. Spot was designed for jobs on Earth first. Mapping factory floors, inspecting dangerous sites, walking into spaces too radioactive for a person to enter. None of that required a spacecraft. It only required legs that could go where wheels could not. Spot carries up to 14 kilograms, about 2 full bags of dog food strapped to its back, and it does that while climbing stairs, crossing gravel, and picking its way over uneven ground that would stop a wheeled machine within a few meters. Cameras cover it on every side, knock it over, and it rights itself, even from fully upside down, the same way a cat lands on its feet without thinking about how. Its top speed is close to 6 kilometers an hour, a brisk human walking pace. A Mars rover, by comparison, tops out around 0.2 of a kilometer an hour, slower than a garden snail crossing a driveway. The gap in what each machine can actually cover in a day is not small. Over a full working shift, Spot could plausibly cross ground it would take a rover weeks to reach. Speed is not Spot's most useful trick. Judgment is. Using its cameras, Spot builds a three-dimensional picture of the ground ahead of it, and works out the safest way over or around whatever is in its path. Nobody steers it in real time. You give it a destination, and it decides the route, avoiding obstacles and catching its own falls in a way that, watching the footage, almost feels alive. That independence is not a novelty feature. It is the only way any of this works. A signal sent from Earth takes several minutes to reach Mars, and several more minutes for a reply to come back. Real-time control never fits inside that gap. Every rover so far has had to make small decisions on its own for exactly this reason. Spot pushes that same requirement much further, choosing its own path across ground nobody on Earth has ever looked at directly. Through a partnership with NASA's Jet Propulsion Laboratory, Spot and a handful of other robots have already been sent into cave systems on Earth, chosen for how closely they resemble what a Martian cave might hold. Pitch dark passages, smoke, dust thick enough to blind a camera, standing water. The robots work through all of it without anyone directing them step by step, choosing their own paths, climbing over obstacles, and recognizing anything worth a second look. Caves are worth that trouble for more than one reason. Cut into a planet's crust, a cave exposes rock a rover would otherwise have to drill through, close to a ready-made cross-section of the ground, cut by nature instead of a drill bit. Everything a drill might spend months reaching is already exposed along the walls, layer stacked on layer, waiting to be photographed rather than bored into. Caves also shelter whatever sits inside them from the slow erosion every exposed surface takes from wind and cosmic radiation, which is exactly why NASA's Braille program wants to know whether bacteria might have survived down there or left some trace behind, sealed away from a surface that erases most other evidence within a few million years. And because that same shelter blocks radiation from above, a cave is also one of the more promising places for a future human colony to actually live, an underground shortcut around the shielding problem the habitat builders are wrestling with elsewhere. None of that is easy to confirm from orbit. Photographs taken from space show, at best, the entrance. What lies beyond it, how far it runs, where it narrows, none of that is visible from above. A wheeled rover would struggle almost immediately. Ground that is uneven or simply not flat. Passages too narrow for a machine over 2 meters wide. And the one problem no amount of careful driving can solve, rock overhead blocking any signal to Earth. The problem does not stop there. Inside a cave, there is no Earth to radio for help even if you wanted to. A cave robot has to explore the whole space with no advanced knowledge of what is inside it, decide for itself how to move through that space, and carry the results back out. That is precisely the problem NASA, JPL, and Boston Dynamics are working on together, combining an onboard decision-making system called Nebula with the Spot platform, sending several robots in as a team, each one relaying what it finds to the others, using cameras and robotic arms to examine anything worth a closer look. JPL and Boston Dynamics compete together as Team Co-Star in the DARPA Subterranean Challenge, a competition built around exactly this task, sending robots into tunnels, caves, and underground urban environments to explore, map, and locate objects or missing people entirely on their own. It is, in effect, a dress rehearsal held underground on Earth for a mission that has not yet been assigned a launch date. The final round ran at the end of September 2021. A strong result, there would be one more sign that walking robots are close to ready for an actual mission to another world. No date has been set for any of these robots to actually reach Mars or the Moon. They are still being tested, cave by cave, here on Earth, but the shape of what is coming is hard to miss. The old story had walking machines crossing the gap between worlds to conquer this one. What is actually being built is the opposite. Machines built on Earth, learning to walk into the dark on their own, so that one day they can help settle a world nobody has lived on yet. The ground they are learning to read is the same ground that will eventually have to feed the people standing on it. Feeding people from that ground starts, oddly enough, with a movie. In The Martian, a stranded astronaut named Watney fertilizes Martian soil with his own processed waste and grows potatoes to survive alone on the planet. The scene stuck with audiences for a reason. It is a simple, almost cozy image. A farmer on a dead world coaxing food out of red dust with nothing but ingenuity. The real question underneath that image is less about drama and more about chemistry. Does Martian soil actually hold what a plant needs? And if something did grow there, would it be safe for a human being to eat? Part of that holds up better than expected. Martian soil does contain many of the nutrients plants require, though not evenly across the planet. Some patches are nutrient-rich, some nutrient-poor. The same unevenness found in soil back on Earth, where a backyard garden bed and a stretch of exhausted farmland can sit only miles apart. But call it soil loosely. It is closer to regolith, crushed rock and dust with no history of worms, insects, or decaying plants folded into it over centuries. On Earth, soil is built by generations of living things dying into it. Nothing has ever lived and died in Martian ground, and nothing has ever rotted into it either. In 2016, researchers tested that gap directly, not with a hypothesis on paper, but with real seeds in real trays. They grew 10 crops: tomato, rye, radish, pea, leek, spinach, garden rocket, cress, quinoa, and chives in soil mixed to imitate the chemistry of Martian ground. The harvest came in only slightly below what the same crops produced in ordinary Earth soil. Not failure, not collapse, slightly less. The same experiment repeated with imitation moon soil told a very different story. Yields there fell by about half, and only spinach really struggled to grow at all. One addition made the Martian result possible, and it was not exotic. Researchers mixed in cut grass, plain organic matter that fertilized the imitation ground, and loosened it enough for water to actually reach the roots. The same way a gardener works compost into tired backyard soil. Without it, nothing would have lasted the season. With it, 10 separate crops came up out of ground built to imitate a planet nothing has ever grown on. So the nutrients are real, and the growing works, on Earth, in imitation dirt. But here's where the ground stops cooperating. Actual Martian regolith carries heavy metals and, worse, calcium perchlorate, a salt that turns toxic once it builds up past a certain quantity. A plant's roots cannot tell the difference between a nutrient and a poison. They draw in both, and from the plant, whatever it absorbed travels straight into whoever eats the harvest. Not a pure poison though, not only a threat. Perchlorate also pulls water directly out of the thin Martian air, water a colony could drink. It can release oxygen too, air a colony could breathe. Poison, water source, oxygen source, all inside the same handful of soil. The same compound sitting in the ground as a hazard doubles as one of the more useful survival chemicals anywhere on the planet. Two problems still stand between that soil and an actual harvest. The first is fertilizer. Watney's fictional solution, his own processed waste, is not far from the real one. Human waste can fertilize real soil, provided every pathogen inside it is killed first, since skipping that step turns fertilizer into a health hazard instead of a resource. Once a farm gets running, compost built from old plants and leftover food takes over the job, and the waste problem solves itself without any more input from Earth. The second problem is the perchlorate, and the fix turns out to be simpler than expected. Not a chemical plant, not exotic filtration equipment. Water rinsed through the soil pulls the perchlorate out, the same basic idea as rinsing salt from a garden bed after a flood. The water and the perchlorate are then separated so neither is wasted. The water reused for the next batch, the perchlorate set aside for the uses that make it worth keeping. A second route exists too. Bacteria that consume perchlorate directly and release oxygen as a byproduct while they do it, turning the same toxin into breathable air on the way out. None of this is a side project for the colony. Growing food is what makes it self-sufficient rather than permanently dependent on resupply shipments from Earth, each one 3 months away at best. Fresh produce, tomatoes, blueberries, and red lettuce among the likely candidates brings real antioxidants into a diet that would otherwise run on packaged rations for years at a time, and fresh food does something for morale that a sealed pouch never will. It may even offer some protection against radiation, though how well that protection actually holds up on Mars, rather than in a controlled lab on Earth, is not something anyone can say with confidence yet. Plants have already proven they can grow almost anywhere they are asked to. In simulated Martian soil, in simulated lunar soil, even in orbit, aboard the International Space Station, nowhere near soil at all. But one question sits underneath every one of those results, and none of them can answer it. Is food grown in actual Martian soil safe to eat? Nobody knows. Nobody can know. Not from a lab on Earth, no matter how carefully the soil is imitated or how many crops come up green in the trays. The only way to find out is to grow it on Mars itself and eat it and see what happens. A working colony would likely run 2 farming systems side by side rather than betting everything on one. Aquaponics, growing plants directly in nutrient-carrying water instead of soil, alongside regolith beds planted in treated Martian ground. The same kind of redundancy the colony would build into its power supply or its water systems, where a single point of failure is never allowed to be the only option. Both systems are hungry for artificial light around the clock, and neither runs itself. Every farm on Mars, whichever kind of dirt or water it depends on, needs daily hands working in it, checking it, coaxing it along. That dirt, real Martian dirt, can very likely feed a colony. Whether it can feed one safely is still an open question, and it is one that no simulation, no imitation soil, no lab on Earth will ever be able to close on its own. Mars itself will have to answer it, and whoever is there to ask the question will be the ones who have to live with the answer. Whoever ends up there to answer that question will be living inside the very systems that made the food possible, breathing recycled air, drinking recycled water, surrounded by the same small circle of faces for years at a stretch. The machines can perform exactly as designed. The arrangement can still be brutal. A colony that is fully self-sufficient on paper is not the same thing as a colony that is easy to live inside. Confined quarters, repeating tasks, the same rations, the same conversations, the same walls, day folded into day with no weather to break the pattern and no door to step outside of. The psychological weight of that is not a footnote. It is one of the harder problems in the whole stack, and unlike regolith or radiation, there is no purely mechanical fix for it. Earth has its own versions of this life, and they are worth holding up for comparison. Antarctic researchers live for months at a stretch in extreme isolation, cut off by weather and distance for the darkest stretch of the polar winter, screened and monitored for their mental health the entire time. Submarine crews do something similar, sealed under the ocean for weeks with no sunlight and no privacy, breathing the same recirculated air as everyone else aboard. Both groups undergo regular psychological checks, because both groups are known to buckle under the strain if nobody's watching for it. But both groups also carry something Mars colonists will not have. Not a base you could evacuate by plane if a researcher broke down. Not a submarine that can simply surface and open its hatch. Nowhere to go. An Antarctic scientist who cannot take it anymore can be flown home within days. A Mars colonist cannot. The trip back, if it happens at all, is measured in months. And for most of the people who go, there may be no trip back planned in the first place. That single difference turns a hard posting into something else entirely, and it means the people who succeed there will need a kind of mental endurance the Antarctic and the ocean floor have never actually demanded of anyone. The mind is not the only thing under strain. The body pays its own price, and gravity is where it starts. Mars holds about a third of the pull Earth does, and the closest thing we have to data on what that does to a human body over time comes from orbit, not from Mars itself. NASA's twin study, built around astronauts Scott and Mark Kelly, one in orbit for the better part of a year while his identical twins stayed on the ground, gave researchers a rare side-by-side look at what near weightlessness does to a body that evolved under full Earth gravity. What it found was not one problem. It was a whole catalogue. Bone density drops. Muscle mass drops with it. Eyesight can change, sometimes permanently. Fluids that gravity normally pulls downward instead pool in the upper body. Balance suffers. The spine, freed from the compression it carries every day on Earth, can shift out of alignment. The heart and the immune system both come under measurable strain. Not one weak point. A body renegotiating almost every one of its systems at once. None of that happened because anything broke. It happened because nothing was asking those systems to work anymore. Muscle and bone are built by a demand. Stop asking a muscle to hold you up against gravity, and the body reads that as permission to let it go, the same way an arm kept in a cast for weeks comes out thinner and weaker than the one that was never immobilized. Mars gravity is not zero gravity, but it is a fraction of what a human skeleton and a human heart are built to work against. Whether a third of Earth's pull is enough to slow that decline, or merely enough to spread it out over more years, is not something anyone can currently answer. We don't know how the body copes with reduced gravity over the length of an entire career on another planet, only that it is not neutral. Exercise is the standard answer, and it works, at least for the timescales already tested. Resistance training and cardiovascular work slow the losses considerably, which is part of why astronauts on long missions already train for hours most days, pulling and pushing against machines built to simulate the load their own weight would normally provide. On Mars, that requirement does not go away. It gets added on top of construction work, farm maintenance, equipment repair, and everything else already filling a colonist's schedule, which means the workday only grows longer. Keeping a body functional becomes a second job nobody gets to opt out of, one with no pay and no end date. But here's where the countermeasures stop being simple. Exercise addresses the symptoms. It does not touch the underlying exposure, and NASA has openly discussed a far more direct answer for astronauts facing years of reduced gravity and radiation, changes to the body itself rather than just its training regimen. Genetic modification aimed at the biology that is struggling rather than the muscles trying to compensate for it. Whether that is plausible with current technology is one question. Whether it should be attempted on a human being at all is a much harder one, and it carries real controversy that this piece will need to sit with properly later. For now, it is enough to know the idea is not fringe speculation. It has already been discussed seriously by the people who would have to approve it. Given everything stacked against a person who signs up for this, cramped quarters, no way home, a body quietly losing ground to gravity it no longer has to fight, longer days, harder questions still unresolved, the volunteer pool has not thinned at all. Every call for astronauts or colonists that space agencies and private companies have put out has been answered by far more applicants than there are seats. Not a trickle of interest, a flood of it, every time. Whatever the honest cost turns out to be, there has never been a shortage of people willing to pay it before they even know the full bill. And the body carrying that willingness to Mars would still have to survive the very thing the exercise and the gene editing talk are both bracing against. The radiation that never stops arriving the whole way there. The radiation that never stops arriving the whole way there has been named 3 times now without ever being explained. It sat behind the case for exercise. It sat behind the talk of changing an astronaut's own biology. It deserves a plainer accounting than a shorthand. NASA has set its own target for the first human landing on Mars at some point in the mid to late 2030s, and almost everything standing between now and that date comes down, eventually, to this one stubborn word. So what is this radiation, actually, that keeps showing up as the reason for longer workdays, stricter dose limits, and harder conversations about changing the human body itself? Radiation, in the broadest sense, is only energy moving through space, in waves or in particles. Most of it is harmless, some of it is necessary. The light reaching your eyes right now is electromagnetic radiation. The warmth from a home heater is electromagnetic radiation too. A microwave oven uses radiation to heat your dinner. A hospital X-ray uses radiation to photograph your own skeleton without opening you up to look. None of that threatens anybody. But there is a second family of radiation, made of particles carrying enough speed and enough energy to strip electrons off atoms as they pass through, and that family behaves very differently. It can tear through the molecules that make up human DNA. In a large enough dose, it causes acute radiation sickness. In smaller doses, spread across months, it quietly raises the odds of cancer years down the line. Same word, describing something that can print a picture of your bones and something that can end your life, depending only on the dose and the type. Two entirely different behaviors, and space asks you to live inside the dangerous one. None of it announces itself. You cannot see a dangerous particle coming. You cannot feel it pass through you. There is no warning flash, no sound, no change in temperature on your skin. A crew member could absorb a damaging dose during an ordinary shift and have no way of knowing until symptoms showed up later. Exhaustion, nausea, cell damage. No onboard medical kit could reverse. That invisibility is part of what makes the problem so hard to plan around. You cannot avoid what you cannot sense, and you cannot ration exposure to a danger that leaves no trace until the damage is already done. The sun is where most of that danger begins, which is an odd thing to say about the same star that keeps every living thing on Earth fed and warm. It gives off a constant outward wind, stripped protons, stripped electrons, and heavier alpha particles, 2 protons and 2 neutrons bound together, charged crumbs of broken atoms streaming outward in every direction at enormous speed. That wind alone is hazardous to anyone standing outside a planet's protection. But every so often the sun does something far more violent. A solar flare, or a coronal mass ejection, an eruption that tears loose from the sun's outer atmosphere, hurls billions of tons of these energized particles outward in a single event. That is more mass thrown into space at once than humanity has launched there across the entire history of spaceflight combined. Imagine standing in the open path of one, with nothing between yourself and the sun. An astronaut caught that way would develop radiation sickness within hours. Solar particles are the radiation most people picture first when they hear the word. They are not the most dangerous kind. Galactic cosmic rays are worse, flung out not by our sun, but by supernovae, stars that finished dying millions of years ago in distant parts of the galaxy. They range from bare hydrogen nuclei, the lightest atom there is, up to nuclei as heavy as uranium, one of the heaviest, every one of them stripped of its electrons and hurled to nearly the speed of light long before it ever reaches the solar system. At that speed and density, a cosmic ray nucleus needs nothing to stop it. It passes through a spacecraft hull. It passes through a human body. It does not slow down. It does not stop. Along the way, it ionizes whatever atoms it happens to touch. Picture a bullet fired through fog. The fog is still there. It simply never gets the chance to matter. Not the sun's occasional temper, then. The quiet, constant rain from stars that died before humans existed turns out to be the harder problem, and it never lets up. Not for a single hour of the crossing. Earth does not face any of this unprotected, and the reason is worth sitting with, because Mars will not share the same luxury. A planet-wide magnetic field, generated deep in Earth's molten core, reaches out into space and bends the paths of incoming charged particles, both the solar wind and a share of the galactic cosmic rays, funneling what does get through toward the poles. That funneled radiation strikes the upper atmosphere there and lights it up. The shimmering curtains of the aurora, a visible signature of a planetary shield doing its work in plain sight, beautiful from the ground and violent up close. The same magnetic field keeps the atmosphere itself from being slowly stripped away by the solar wind, the way Mars's own atmosphere likely was, thinned over billions of years until only a fraction was left. And the atmosphere that survives on Earth, thanks to that shield, does a second job of its own. It collides with whatever cosmic radiation slips past the magnetic field, absorbing most of it before it ever reaches the ground. A traveler standing on the surface of Earth is protected twice over without ever noticing either shield working. Nobody wakes up grateful for the magnetic field. Nobody thanks the atmosphere on their way to work. Both have simply always been there, doing their job in silence, for as long as anyone has been alive to take them for granted. Two defenses, stacked one behind the other, and neither one exists on Mars. No global magnetic field to bend the incoming particles towards safety. A sliver of atmosphere, a small fraction of Earth's, catching only a small fraction of what does get through. Everything that shields a person standing on Earth for free would have to be built by hand on Mars, or done without entirely. None of that protection rides along with a spacecraft on the way there, and none of it is waiting on the ground once you land. Replacing it, piece by piece, with mass and water and buried regolith, instead of a planet's own magnetic field, is the harder problem still to come. And that problem starts the moment a crew leaves Earth's shadow, long before anyone reaches the ground to bury a habitat at all. Everything Earth does for free must now be built by hand, or done without entirely. That was the hard truth, sitting at the end of the last problem. The harder question follows right behind it. If the shield is gone, what do you actually put in its place? From the moment a ship leaves Earth's shadow, to the day boots finally touch Martian ground, and for every single day a person spends standing on that ground afterward. Start with the trip itself. Reaching Mars realistically takes at least 100 days, and a crew is exposed to space radiation for every one of them, awake or asleep, working or resting. There is no shift where the exposure clocks out. The spacecraft's own structure does stop something. Almost all of the particles thrown out by solar flares and coronal eruptions never make it past the hull. But the galactic cosmic rays, the ones flung out by supernovae that finished dying millions of years ago, pass straight through metal the way they pass through anything else, hull or no hull. Recent rover missions have measured what a crew would actually absorb making that crossing. About 0.66 sieverts, a unit doctors use to track how much radiation a body has taken on. Put in terms anyone can picture, that comes out close to a full-body CAT scan every 4 or 5 days for the whole trip, month after month, with no days off. Standing on Earth over that same stretch, a person absorbs something like 0.025 sieverts. Divide one figure by the other, and the crossing delivers well over 200 times what a person on Earth would take on over the identical stretch of calendar. The gap between those two numbers is the entire problem. In miniature, the obvious fix is mass. Enough material between a person and the radiation, and almost anything can be blocked. That much has been true since the earliest reactors on Earth. But mass is exactly what a rocket cannot afford. Every extra kilogram bolted onto a spacecraft's walls has to be lifted off Earth's surface first, fought against gravity the entire way up, and that cost multiplies fast the higher it climbs. A heavier hull is not a free upgrade. It is a different, more expensive rocket altogether. NASA's Orion capsule has tested a cheaper workaround for the worst moments instead. During a period of unusually high radiation, the crew retreats into a small, makeshift bunker built out of stacked supply bags, food, water, equipment, anything dense enough to soak up a dangerous spike until it passes. Nothing about the bunker is elegant. It is closer to sheltering behind furniture than to any purpose-built shield, and it works anyway, because density is density, wherever it comes from. For the rest of the trip, the answer leans on one particular element. Hydrogen blocks galactic cosmic rays better than almost anything else tested, so engineers are experimenting with storing drinking water inside the walls of the crew compartment itself. The same water doing two jobs at once, hydration and shielding, with nothing extra launched to carry the weight. A newer idea carries the same principle into fabric. Suits woven from or lined with hydrogenated boron nitride nanotubes, tube-shaped molecules only a few atoms wide, carry protective hydrogen atoms throughout their structure while staying strong enough to double as spacecraft skin and tough enough to survive extreme heat. The same material, in theory, could clothe a person and build the hull around them. Whether it performs as hoped outside a laboratory is still being tested. One more idea goes further than simply blocking particles. Build an actual magnetic field inside the ship, a small copy of the one Earth generates for free, deep in its own molten core, and let it bend incoming particles aside the same way the planet already does for everyone standing on its surface. Such a field can be built. It cannot yet be built efficiently enough to run without draining every other system dry. Perhaps by the 2030s, that energy problem gets solved. It has not been solved yet, and that is the same gap in the same idea raised earlier, back before liftoff was even a settled question. A shrunken magnetosphere wrapped around the whole ship. It remains exactly as unsolved now as it was then. None of that changes what actually happens at the hull today on any ship that could be built right now. Solar particles, stopped. Galactic cosmic rays, not stopped. Not by ordinary metal. Not by anything built into the walls yet. A crew crossing to Mars survives the trip, hiding behind stacked bags and water tanks, not behind the ship itself. Arriving does not end the exposure. It only changes its shape. Mars has no magnetosphere at all, and its atmosphere is a sliver of Earth's. So surface protection is real but thin. Better than open space. Nowhere close to home. Altitude helps a little. Lower ground means a slightly thicker blanket of air overhead. One more reason low. Water-rich terrain kept winning out over higher, drier ground. Even so, surface exposure comes out to about 0.64 millisieverts every single day. A dose close to a dental X-ray repeated without pause, day after day after day, and that daily total already sits just over the limit most agencies consider acceptable, before a single flare or eruption adds anything on top. The plan, then, is not to leave anyone standing exposed on open ground waiting for the numbers to add up against them. Those earlier robot-built habitats, printed from regolith and buried under still more regolith, do the real work here. Piled Martian dirt, thick and heavy enough, blocks most of what reaches the surface, especially the sudden, dangerous spikes thrown off by a coronal mass ejection. A fleet of NASA spacecraft already watches the sun for exactly that kind of eruption, reading its outbursts from millions of miles away and giving any astronaut caught outside enough warning to get back under cover long before the particles arrive. Stack it all up. Water walls, nanotube suits still being tested. A magnetic field that works in principle but cannot yet run. Buried regolith and an early warning system watching the sun. None of it is one clean solution. All of it together is closer to a patchwork than a shield, stitched from whatever partial answer happens to be ready. Whether that patchwork can ever add up to a body that is truly safe, on the crossing or on the ground, is a question engineering alone has not answered, and nobody building any of these pieces claims otherwise. The next attempt at an answer would not come from a wall, a suit, or a magnetic field at all. It would come from inside the body itself, not the ship's hull, not a suit lined with exotic fiber, not a shield stacked from bags of rice and water. If the trip to Mars cannot be made fully safe by anything built around a person, the next attempt at an answer looks at rewriting the person instead. That sounds like something out of a novel, engineered astronauts with borrowed resilience built into their cells. It is not fiction. NASA has already begun looking seriously into gene editing for the crews it hopes to send. And the closer engineers look at what radiation actually does to a human body over the course of a Mars mission, the less optional the idea starts to feel. This is where the piece stops asking how to protect the traveler, and starts asking whether the traveler needs to change. Start with what radiation already does to a body that never leaves Earth. Rock underfoot and cosmic rays filtering through the atmosphere give every person here a small, steady yearly dose, somewhere around 3 millisieverts a year. A single millisievert is roughly equal to 3 chest X-rays. Spread out across 12 months, the body barely notices. It has time to repair what little damage slips through before the next dose arrives. Step outside the magnetosphere and that quiet arithmetic breaks. Simply standing on the surface of the moon multiplies the dose by 200. Solar particles and background cosmic radiation pass straight through an unprotected body the way they pass through an empty room, tearing at DNA as they go. The short-term symptoms look like a bad flu, fever, nausea, vomiting, misery that passes in days. The long-term ones do not pass. Cancer, sterility, damage that shows up years after the mission is a memory. Every space agency sets a hard ceiling on how much of that damage one person is allowed to absorb across an entire career. The number usually lands around 1,000 millisieverts, a limit built from decades of studying what a human body can take before the risk of long-term harm becomes unacceptable. Cross it, and an astronaut is grounded for good, no matter how healthy they still feel standing in front of the doctor. Here is the uncomfortable part. Even with every shield engineers can currently build into a spacecraft, a round trip to Mars and back could still deliver as much as 1,200 millisieverts. That is over the lifetime limit before the mission has even finished. Not a career with room left for a second flight. A career closed out in one trip. In chest X-ray terms, that single round trip is worth something like 3,600 of them, absorbed continuously, with no healthy year in between to recover. And Mars is not even the harshest destination on the list. A colonist working the surface of Europa, the icy moon orbiting far past Mars, would take on 5,500 millisieverts in a single day. At that dose, the odds of dying within the next month are close to a coin flip. None of that erases the reason for leaving in the first place. The sun still becomes a red giant in roughly 6 billion years, swallowing the inner planets whatever anyone decides about radiation limits. A planet-ending asteroid is still, statistically, overdue. A species that lives on only one world remains a species one bad day away from ending entirely. That was the case for going at all, made at the very start of this journey. The radiation numbers do not weaken that case. They only make clear that surviving the trip cannot rest on shielding alone, and that the body making the journey may have to change along with everything built around it. On August 13th, 2021, NASA announced it had tested exactly that kind of change aboard the International Space Station. Researchers deliberately broke a strand of yeast DNA, cut out the damaged section, and spliced in a healthy replacement, using a gene editing tool called CRISPR, a method for finding a precise stretch of genetic code and swapping it out. It is not unlike replacing a puncture on a tire instead of throwing out the whole wheel. Since radiation damages DNA in exactly this way, a strand torn and broken in specific places, the ability to cut out the damage and patch it back in gives astronauts a form of ongoing genetic maintenance, repairing harm as it accumulates instead of waiting for a diagnosis years after the fact. CRISPR does not stop at repair. The replacement material does not even need to match the original sequence. Scientists have already used it to implant entirely new genes into test subjects, genes that were never there to begin with. For sickle cell anemia, a disease that leaves the blood short on healthy hemoglobin, CRISPR can remove the faulty genes responsible and replace them with working ones instead. Trials in human patients are already underway, and the early results are encouraging. If CRISPR can move genes between two people, it can also move them between two species entirely. Tardigrades, sometimes called water bears, are microscopic animals barely visible without a microscope, and they shrug off conditions that would kill almost anything else, including radiation, complete dehydration, and the vacuum of space itself. They survive it because of a protein they produce called D-ZUP, short for damage suppressor, which behaves something like a molecular repair crew, gathering around a cell's DNA and standing between it and the particles that tear other organisms apart strand by strand. In 2015, geneticists took the gene responsible for producing D-ZUP out of a tardigrade cell and edited it into a culture of ordinary human cells growing in a lab. Those human cells became 40% more resistant to radiation than untreated cells sitting right beside them. Not a modest improvement, close to a near doubling of what an unmodified human cell could withstand on its own. None of this is as simple as it sounds, and the source material behind it is honest about why. Genes rarely do just one job. A single gene can influence several traits at once, so editing it in the hope of one benefit can ripple outward into effects nobody predicted. Some helpful, some not. Most still unmapped. Introducing a tardigrade gene into a human genome has to happen slowly and carefully. one tested step at a time, not as a single sweeping rewrite performed on faith. Over years, scientists expect to map out what each gene actually does on its own and in combination with the others around it, and how to balance the trade-offs that come with changing any one of them. That patience is not caution for its own sake. It is the only responsible way through a system this tangled. And even once the how is worked out, a harder question sits underneath all of it. Should any of this be done at all? Repairing damage or curing a disease that already has a name and a diagnosis is one thing, and most people accept it without much argument. Deliberately redesigning a person before they are even born is another question entirely. That line has already been crossed, not in theory, but in a delivery room. In 2018, a doctor in China announced the birth of 2 genetically edited infants, given the names Lulu and Nana, altered before birth to resist a strain of HIV. He had told almost no one what he was doing. Within days of the announcement, his government shut the work down. By 2019, he was in prison. The technology to rewrite a human being did not wait politely for the ethics to catch up first. Some of it is already loose in the world, born and breathing, and the question of how far this goes and who gets to decide is only getting louder from here. Repairing damage is one thing. Handing an astronaut a healthy gene in place of a broken one is still, at its core, medicine, even if the tool doing the work feels new. There is more to it than that. The same tool does not stop at repair. Once a gene can be swapped out, it can also be written in from nothing, built new for a body meant to live somewhere Earth never prepared it for. Editing every cell in a person, not one organ or one patch of skin, remains a distant prospect. Nobody is close to doing it yet, and nobody claims otherwise. But suppose it eventually arrives. It would not just mend people, it would reshape what a person could be, one hostile world at a time. Take a colonist bound for Mercury, scorched on the side facing its sun, or for Pluto, cold enough to freeze the very air that leaks from a cracked seal. Worlds far hotter or colder than anything a human body currently tolerates for more than a few unprotected minutes. Certain bacteria on Earth already hold together inside solid ice, quietly persisting in cold, that would stop almost any other living thing within minutes. Borrow whatever lets a microbe do that, and a body could in principle hold its shape somewhere the cold currently wins outright. No suit required to argue with the weather. Pluto raises a second problem that has nothing to do with temperature. Out there, sunlight arrives as little more than a rumour of daylight, a dim smear where a sun ought to be. A body built for it might carry eyes enlarged to gather whatever light exists, the way a nocturnal animal's eyes already do back on Earth. Or it might trade eyes for something else entirely, closer to what a bat or a dolphin already carries. Sound sent out into the dark and read back as shape, a way of finding your way that asks nothing of the light at all. Neither is imaginary biology. Both already exist, just not yet in a human. Water poses its own version of the same question. Genes borrowed from fish could let a person pull oxygen straight out of water through something built like gills, breathing the way a fish already does, without a second thought. On Earth, that could ease crowding on dry land by opening the oceans back up to people. Out among the stars, it could open entire ocean worlds, moons hiding liquid seas under miles of ice. To the same trick, long voyages ask for something else again. A ship crossing the distance between stars, even one far faster than anything flying today, could still take centuries to arrive, longer than any single life now runs. A traveler able to hibernate through that stretch, sleeping the decades away the way a bear sleeps through a single winter, or one who simply needed far less food to keep going, would change what a long trip even means. One proposal goes further still. Fold chloroplasts, the tiny structures inside a plant's cells that turn sunlight into food, into human skin, and a traveler could feed quietly on daylight the way a leaf already does, topping up on a walk outside instead of at a dinner table. Sensors could be next. A hammerhead shark reads the faint electrical field given off by another living thing nearby, sensing a hidden fish the way a person might feel a draft under a door. Push a person's eyes past what they already see, into X-rays, into the heat an object gives off as infrared, and the radiation pouring out of an oncoming solar storm becomes something a traveler notices coming, rather than something measured only after the fact. Once the damage is already done, diet could stretch too. Certain worms already break down plastic as food, turning waste into fuel for their own small bodies. A body able to do the same would solve a garbage problem twice over. Once on a crowded Earth drowning in what it throws away, and again on a colony with nowhere at all to send its trash. Longer life, sharper thought, patience for problems that outlast a single career. All of it sits inside the same catalogue. Every trait any species has ever evolved, available in principle to whoever eventually learns how to borrow it correctly. The answer was stranger than expected. The borrowing might one day stop being necessary at all. Christopher Mason, a geneticist who has worked with NASA on 7 separate projects, argues in his book, The Next 500 Years, that a person's genes could eventually be written from scratch rather than borrowed from anywhere, and switched on and off like a light in a room, a trait turned on for one winter's voyage, and quietly retired once it is no longer needed. None of this is offered as a warning. People already adapt, generation after generation, in perfectly ordinary ways, and none of it required asking permission first. But once a body's traits become something ordered on request rather than simply inherited, the question underneath it all stops being technical. What actually makes someone human? Not the shape of a face, not the senses a person happens to carry, not even the genome sitting inside every cell, not once that genome answers to instruction instead of chance. At first, only the wealthy would likely afford any of it, the way any new medicine starts expensive before it spreads. Give the idea 1,000 years, roughly the span since the oldest cathedrals still standing were first raised stone by stone, and it could be ordinary enough that children study which of their own genes to change as schoolwork, the way a child now studies arithmetic. Faces, senses, entire body plans could drift apart from each other the longer this continues. Some of it chosen for survival on a hostile world, some of it chosen the way a person now chooses a haircut, for no reason beyond wanting it. Wings, for the look of them. A tail, for no reason beyond wanting one. The same tool that lets a colonist survive Pluto could just as easily become fashion. Spread across enough worlds, adaptation like this would not stay cosmetic for long. A population shaped by Mercury's heat, and a population shaped by Pluto's dark could, given enough centuries apart, stop resembling each other at all. Not physically. Not in what their bodies can even do anymore. Not one species carried out to the stars. Several descended from one that started here, on one crowded, blue-green world, before anyone left. Whether any of that ever happens depends on machines that do not yet exist to carry anyone that far in the first place. Those machines are already being built, and closer to home than any of this suggests. All of that lies centuries away. The machines that might begin any of it are being built and flown today by a surprisingly small number of people. Richard Branson and Jeff Bezos became the first billionaires to fly into space on vehicles built by their own companies. A shift as much about who is doing the building as who is doing the flying. For most of the space age, a rocket meant a government, not a company, not a founder riding the machine his own money built. Commercialization is not new, exactly. In 1962, 5 years after the Soviet Union put the first artificial satellite into orbit, the American telephone company AT&T launched the first commercial satellite, Telstar 1, to carry American television across the Atlantic to Europe, riding on a NASA rocket built by someone else. In 1975, a company called OttRag, founded in Stuttgart, Germany, became the first to develop its own alternative rocket propulsion system. In 1984, the American president signed the Commercial Space Launch Act specifically to encourage companies into this business. Satellites have quietly run the practical side of space for decades. The navigation in a car, the signal behind a phone call. What changed is newer and sharper than any of that. Private companies now design their own rockets from the ground up and put their own founders inside them. That is the turning point. A tourism industry, paid for by wealthy passengers, is the first visible result. 3 companies show 3 different answers to the same opportunity, and the differences between them turn out to matter more than the fact that all 3 exist at all. Branson won the race to fly first on July 11th, 2021, though he had founded Virgin Galactic back in 2004. The company he founded did not build its own spacecraft to start. It watched another firm scaled composites, chased the Ansari X Prize, a competition for the first privately built crewed spacecraft, and Branson signed on as their future customer. The bet paid off. On October 4th, 2004, the resulting craft, Spaceship One, climbed to 112 kilometers and returned its crew safely. Space is officially considered to begin at 100 kilometers, a boundary called the Kármán line, named for Theodor von Kármán, the first person to seriously try to define where the sky ends and space begins. NASA draws its own line lower, around 80 kilometers. Spaceship One crossed both, not by a narrow margin, with more than 10 kilometers to spare above the stricter of the two lines. Virgin then built a fleet of successor craft and founded a company to manufacture them, first as part owner, later buying the whole thing outright. The aim was never orbit. It was 6 passengers and 2 pilots, lifted just high enough to see the planet curve away beneath them, and feel, briefly, nothing pulling on their bodies at all. The method is almost gentle by rocket standards. A carrier aircraft lifts the spacecraft to 15,000 meters, about the cruising height of a very high altitude jet, and releases it. The rocket motor ignites, reaching supersonic speed in about 8 seconds, climbing past 80 kilometers. The climb takes roughly an hour. At the top, the engine cuts out and gravity takes over, and for about 5 minutes the passengers float, weightless. The way a ball thrown straight up hangs for an instant at the peak of its arc, neither rising nor falling. Then a feathered re-entry system, wings that fold to slow the fall like a shuttlecock, glides the craft home over about another hour. A 2-hour round trip, door to door. The ticket price is $250,000. Jeff Bezos took a slower, quieter road to the same sky. He has said he was fascinated by space since he was 18, imagining space hotels, amusement parks, and orbital colonies holding somewhere between 2 and 3 million people. Less as tourism than as a way to move heavy industry off a crowded Earth. He founded Blue Origin in 2000, funded privately, and kept almost entirely out of public view. The company bought land in 2003 while outsiders wondered what it was for, where Virgin Galactic courted investors and headlines from the start. Blue Origin worked in near silence. Not a press release, not an investor pitch. A land purchase nobody outside the company could explain, for roughly a decade, until a NASA contract arrived in 2009, and the company finally opened its doors publicly in 2015. Its first rocket, New Shepard, named for Alan Shepard, the first American in space, is also built for tourism, but Bezos has been clear it is meant as a beginning, not an end point. In a 2016 speech, he compared the space industry to the earliest days of aviation, when thrill-seeking passengers willing to pay for a novel experience quietly built the market and funded the technology that eventually put a plane ticket within reach of nearly everyone. New Shepard's passenger capsule detaches and climbs past the Kármán line, higher than Virgin's craft, to around 107 kilometers, and moves faster too. The entire trip lasts about 11 minutes, against Virgin's 2 hours, for a similar price. Bezos is already naming what comes next. New Glenn, aimed at true orbit. New Armstrong, after that, aimed at the moon. He has said much of Earth's heaviest industry will eventually move off-planet, though not, by his own admission, within his lifetime. But here's where the race stops being about tourism at all. Elon Musk founded SpaceX in 2002 with almost no interest in flying passengers for a view. He wanted cargo, and lots of it, and the company now holds roughly half of all commercial satellite launch contracts, largely because its workhorse rocket, the Falcon 9, is reusable. Virgin Galactic and Blue Origin, for all their engineering, never leave the neighborhood of the sky for long. Neither reaches true orbit. Not once, not yet. SpaceX does, routinely, and that difference is not a matter of degree. It is the difference between a carnival ride at the edge of the atmosphere and a cargo run that actually goes somewhere and comes back for more. A reusable rocket does not have to be built from scratch every flight, and that single fact collapses the cost of reaching orbit. The Falcon 9 dwarfs the other two companies' vehicles, standing about 70 meters tall against roughly 18 meters for New Shepard or Spaceship Two. Its engines are built to reach orbit outright, not brush past the edge of the atmosphere and fall back. It carries a reusable cargo capsule, Dragon, the first of which delivered supplies to the International Space Station, and it can lift 5,500 kilograms into orbit, more if the rocket is flown once and discarded rather than recovered. That cargo number matters more than it sounds. A rocket that can move heavy weight cheaply between orbits is also, in principle, a rocket that can move heavy weight to Mars, and any Mars colony will need supplies shipped from Earth for a very long time. A company that can deliver freight between planets stands to profit enormously from exactly that need. Musk has said for years that a Mars colony was always the actual goal. As far back as 2001, his company sketched plans for greenhouses to grow food there, and that same year, he tried simply to buy rockets from someone else to start moving supplies toward Mars. Building his own turned out to be cheaper. SpaceX is now valued above $75 billion. Its next vehicle, Starship, is designed to reach the moon and, further out, carry 100 tons of cargo to Mars, refuel once it lands, and fly itself back. The transit for that trip, under current plans, is roughly 6 months. Tourism, lunar landings, orbiting facilities, refueling stations on another world, freight runs to Mars. Every one of these remains, for now, a stated goal rather than a finished achievement. But 3 private companies have already done what only nations used to do, and done it inside 2 decades, which is exactly why the goals no longer read as fantasy. Reusable rockets already fly. Founders have already ridden their own machines past the edge of the sky. The road to an interplanetary species runs, at the moment, through a small handful of companies racing each other toward the same horizon. And the machines carrying that race forward are the same machines that will eventually have to survive the planet waiting at the other end of the trip. Suppose every rocket in that race actually succeeds. Suppose the freight lands on schedule and the first colonists step out onto ground finally worth walking on. The planet still has one thing left to say about all of it, and it says that in dust. From orbit, Mars looks calm. Flat plains, scattered rock, a horizon the color of rust under a thin, quiet sky. A faint wind stirs the top layer of grit, and little else. By every visual cue, this looks like one of the stillest places human eyes have ever studied. Not always, not for long. Roughly once every 3 Martian years, about 5.5 years by an Earth calendar, long enough for a child born the day one ends to be starting school by the time the next one begins. That stillness breaks. Somewhere on the surface, a wall of dust starts rising and does not stop. It does not stop at a canyon. It does not stop at a mountain range. It does not stay confined to one hemisphere. It swallows the entire planet. Light drops for weeks, sometimes for months. Machines built to run on sunlight go dark, and much about why this happens at all is still not fully understood. To see how a calm planet gets there, start further back, with the air Mars used to have and lost. Mars was not always this dry. Billions of years ago, it held a thicker atmosphere, thick enough to keep water flowing across the surface as real rivers and most likely real lakes, and warm enough that ice was not the planet's only form of water. Over that vast stretch of time, the atmosphere thinned and bled away into space, stripped particle by the solar wind, slowly and relentlessly, until what remained was less than 1% of the air pressing down on Earth right now. If Earth's atmosphere filled a bathtub, what is left on Mars would not fill a coffee cup. The rivers dried into the channels that rovers now drive across, and the planet that is left runs on a version of weather almost nobody would recognize. Thin air is bad at holding on to heat, and Mars pays for that every day. Carbon dioxide makes up most of what remains, and carbon dioxide is good at trapping warmth. Molecule for molecule, it holds heat better than the nitrogen and oxygen that fill Earth's sky, but there is so little air overall that the advantage barely matters. A blanket made of the best insulating fiber in the world still fails to keep you warm if it is only a few threads thick, and that is close to what is happening here. There is simply not enough air overall to keep the day's warmth from escaping once the sun goes down. Stand at the equator during the warmest hour, and the ground beneath your boots might read close to 23 degrees Celsius. Lift your head and the air around your helmet is closer to freezing, near zero, warm at your feet, cold at your collar, two climates, one body, at the same moment. That gap is nothing next to what happens between noon and midnight. Daytime highs near 27 degrees Celsius fall, by night, to nearly minus 133, colder than anywhere on Earth ever gets, by a wide margin. Temperature differences like that do not sit still. They drive wind, the same basic mechanism that drives weather on Earth. But Earth's weather runs on water, rain, evaporation, cloud. Mars gave that cycle up along with its thick air. What is left runs on dust instead. Without dust in the mix, a planet-swallowing storm would probably never form at all. Dust enters the Martian air by two main routes. The first is the dust devil, and Mars makes thousands of them every year, mostly through its spring and summer. The ground heats first under the sun. The air just above it heats with it and starts to rise. Cooler air rushes down to fill the space that leaves behind, and the two currents twist against each other into a spinning column. Some rise only a few meters. Others reach widths of hundreds of meters, several football fields laid end to end, and climb as high as 8 kilometers, nearly the height of Everest standing on its end. Each one drags dust upward as it spins, and even after it collapses, some of that dust stays behind, thickening a faint haze that never fully clears. On any ordinary day, that haze is the whole story. A background dimming of the sky, nothing more dramatic than that. The second route lifts far more dust, and it works backward from what you would guess. Wait, the wind lifts the heavy grains first, not the light ones. Light dust clings to itself, held together by a faint electric charge, the same clinginess that makes packing peanuts stick to a sweater instead of falling free. Wind has to work harder against that clinginess than it does against something heavier. Heavy dust does not have that problem. A gust picks up the larger grains easily, drags them a short distance and drops them again, too heavy to stay airborne. But every landing is a small impact, and every impact knocks loose the fine, clingy dust sitting nearby. The heavy grains do the wind's work for it. Wind lifts sand. Sand knocks dust loose. That process has a name: saltation, and it is the single most important route dust takes into the Martian sky. Once a grain of dust actually gets airborne, Mars is generous about keeping it there. Low gravity lets dust drift for weeks, sometimes months, before it settles again. And while it drifts, it changes the air around it. Thin Martian air is poor at grabbing the sun's heat directly, but suspended dust is very good at it. Each particle acts like a tiny radiator, soaking up sunlight and releasing that warmth slowly into the surrounding air instead of letting it pass straight through to the ground below. Warmer air rises. Rising air pulls in wind from every side to replace it, wind stronger and wider than anything a single dust devil produces. That wind kicks up more saltation. More saltation lifts more dust radiates more heat. Each step feeds the next, the way a small flame can climb from a single dry branch to an entire hillside if nothing interrupts it. And a small local disturbance stops staying local. It becomes a regional storm, still growing, still feeding itself, with no obvious point where it has to stop on its own. What began as a few grains bouncing across open ground is, by this point, capable of swallowing weather systems the size of continents. And on a planet that started this whole story looking perfectly still, that is only the shape the trouble takes before it turns into something a colonist would actually have to survive. Grow that same feedback loop large enough, and continent is not the ceiling. Scale is not proof of violence, though. On a local level, a Mars dust storm is close to harmless in itself. Wind speeds top out around 97 kilometers an hour, roughly half the top speed of a hurricane back on Earth, and close to a speed you would recognize from a fast stretch of highway. That sounds quick until you remember how thin the air actually is. A single gust here carries a fraction of the punch it would on Earth, the same way one person pushing against a door moves it far less than a whole crowd leaning on it together. Despite what the movies show, a Martian dust storm cannot topple a spacecraft. It cannot crack a satellite dish. It cannot flatten a habitat. Not a wrecking force, a dimming one. So what does a storm capable of swallowing a planet actually do, if not tear anything apart? The real danger was never the wind. It was the dust itself, settling, Any rover or lander running on solar power sits exposed to a slow, sticky coating of electrostatic dust, grain by grain, day after day, until the panels underneath stop collecting enough sunlight to keep the batteries charged. There is no impact, no crash, no single dramatic moment. Just a fine layer thickening on glass that used to be clear. That quiet accumulation alone has already ended more than one mission. And once a storm starts building, it rarely stays local. Mars's orbit is not a perfect circle. Each year, around the start of Southern Hemisphere spring and summer, the planet swings closest to the sun and picks up the most warmth. And for reasons nobody fully understands, scattered regional storms start merging into something the size of a continent. It could be coincidence, storms simply piling up where the heat happens to be strongest, each one unrelated to the last. But the timing repeats every single year, on schedule, like clockwork. The same season, the same warmth, the same merging. Coincidence stops being a satisfying answer once something happens on a calendar. Above the continent-sized storms sits a rarer, stranger tier. Roughly once every 3 Martian years, close to 5.5 years by an Earth calendar, the same interval the last section measured against a child starting school, a storm stops being regional and becomes planetary. That interval is too short to blame on Milankovitch cycles, the slow astronomical wobbles that reshape a planet's climate over tens of thousands to hundreds of thousands of years, so that explanation is ruled out before it even gets started. Something in the dust cycle itself seems to need that much time to reset and build toward another giant storm, as if the planet was slowly recharging between eruptions. What that something actually is remains, honestly, unknown. We don't know yet. Nobody does. Most dust storms last only a few days, blowing through and clearing on their own. The planet-swallowing kind can last weeks, sometimes stretching into months before anyone sees blue sky again. Scientists gauge just how bad one has gotten with a measurement called aerosol optical depth, a number for how much sunlight gets blocked or scattered by the particles hanging in the air. On an ordinary Martian day, that number sits around 0.5. A rover like Opportunity or a stationary lander like InSight needs it below 2 just to keep its batteries charged through the day. Thick wildfire smoke on Earth, the kind that can turn noon into midnight, measures around 7. A planet-sized Martian storm reaches 9 to 11. Almost no light gets through at all. In 2018, a storm of exactly that size killed the Opportunity rover. Dust swallowed its solar panels first, then its batteries. Its onboard heaters exist for one reason: to keep delicate electronics from freezing solid through the long Martian night. And with no power left to run them, the wild swing between Martian day and Martian night cracked something essential inside it. It never woke up. Nuclear-powered rovers fare better, but are not spared entirely. Curiosity does not depend on sunlight, but even it goes quiet when a storm this thick rolls over, because the same cloud that blocks light also blocks the radio signal home, the way rock once blocked signals inside a cave. Scientists on Earth can only wait. Satellites overhead have their own bill to pay too. All that heated, suspended dust puffs the whole atmosphere outward into the paths where satellites orbit, and each one has to burn its own fuel-correcting course, so the extra drag does not slowly pull it down. Fuel that, once spent, cannot be resupplied from the ground below. For an actual settlement, this stacks into something worse than an inconvenience. A colony running on solar power alone would have no other option once the sky went dark for weeks on end. The cold outside would only get worse with no sun left to warm the ground. And losing contact with Earth during exactly the event most likely to need outside help would leave colonists to handle whatever went wrong entirely on their own. The same self-reliance the crossing itself already demanded of them, long before the first storm ever arrived. But the same process that builds these storms also ends them. Block enough sunlight and the ground beneath it stops warming. Stop warming the ground and the rising air that lifts new dust stops rising. No more updrafts. No more saltation. No more fuel for the storm to feed on. The very darkness the storm creates is what finally starves it. A storm this size effectively suffocates itself on its own success. Quiet returns. Surviving rovers wake from hibernation once the sky clears and the signal home comes back, and whatever work was paused simply resumes, as though the planet had only been holding its breath. As of 2023, 3 rovers are still out there working. NASA runs Curiosity and Perseverance. China runs Zhurong. Only Zhurong depends on solar power, so only Zhurong has to keep one sensor turned toward the sky at all times. The last planet-wide storm was in 2018. At roughly one every 5.5 years, the next one is not far off, somewhere out past this moment, gathering itself the same unremarkable way everyone before it has. It will start the same way this one did, and the way the very first moment of this story did too. Calm plains, a rust-coloured horizon, a thin, quiet sky, and somewhere out past that horizon, a little wind stirring the top layer of grit, patient, unremarkable, and not staying that way for long.